a matrix is equal to its own transpose, then that matrix is called a symmetric matrix. Here in this video, we study various properties of real symmetric matrices. And one of the interesting properties is this. Any symmetric matrix can be diagonalized like this by an orthogonal matrix, and all the eigenvalues are real. And there are other interesting and useful properties of symmetric matrices. So let's start. Okay, so the first property we study about symmetric matrices is this. Let A be n by n real symmetric matrix. Then for any vectors x and y, n-dimensional vectors, we have the following. The inner product between ax and y is equal to the inner product between x and ay. So that means the place of a can be switched. To prove this, it is useful to note the following property about the inner product. So any inner product between x and y can be considered as the matrix product between x transpose and y transpose. Here, a row vector x transpose is interpreted as 1 by n matrix, and the column vector y is interpreted as n by 1 matrix. And of course, this is also equal to y transpose times x. Okay, noting this, let's consider this inner product between ax and y. So this is equal to ax transpose times y. But the transpose of a product is the product of transpose with each factor reversed. So x transpose times a transpose and y. And since matrix multiplication is associative, we have now a transpose y here. But this is equal to the inner product between x and a transpose y. So up to this point, we have assumed nothing about a, but a is actually symmetric, so a transpose is equal to a. And we are done. Next, we want to prove that all the eigenvalues of a real symmetric matrix are real. But what are eigenvalues anyway? For any matrix A, if it satisfies the following equation, ax for some vector x times lambda, lambda is a scalar, times x, then this lambda is called an eigenvalue. And this vector x is called the corresponding eigenvector. Okay, now, assuming A is real symmetric, then we can prove that all the lambda, any lambda that satisfies this, is real. And of course, then the corresponding eigenvector contains only real elements. Now, let's assume A is a real symmetric matrix, and it has an eigenvalue lambda and the corresponding eigenvalue u. Okay, so lambda is an eigenvalue of A, and u is the corresponding eigenvector. And now, let's take the complex conjugate of both sides. Then we have a u star. Star means complex conjugate of all the elements, and lambda complex conjugate and u complex conjugate. Because we're assuming A is real, the complex conjugate of A is just A itself. Okay, now then consider this lambda times inner product between u star and u. Okay, and this is equal to the inner product between u star and lambda u, because we can move this scalar inside. And since lambda is an eigenvalue of A, so we have this equation, So u star times a u. Now, from what we have proved before, this A, this place of A can be switched to the first component of the product. Now, we have this equation now. So that means this A U star is equal to lambda star U star. But this scalar lambda can be taken out. So now we have this. Now let's consider the elements of the vector u. So let's write it explicitly. We have something like this, and its complex conjugate will be u1 star up to un star. Okay, so u1 star is the complex conjugate of u1 and so on. So the inner product between these two vectors becomes this: u1 star times u1 and so on up to un star times un. But u1 times u1 star means the modulus of u1 squared and so on, and modulus, so complex modulus, right, of un squared. And since the eigenvector cannot be the zero vector, so this must be greater than 0, strictly greater than 0. Okay, so now let's go back to this equality. So from here, we have lambda minus lambda star times the inner product between u star and u is equal to 0. But this part, this inner product, is non-zero. Therefore, lambda must be equal to lambda star, which means lambda is real. And we are done. Next, we prove yet another important property of real symmetric matrices. Suppose A is, as usual, real and symmetric, and it has an eigenvalue u, eigenvector u, and eigenvalue lambda. And it also has another eigenvector and eigenvalue, v and mu, let's say. And if lambda and mu are different, then the eigenvectors u and v are orthogonal to each other. So let's prove this, and again let's consider this inner product, lambda times, let's say, u v, inner product between u and v, and put lambda inside. Let's first put it here, and lambda u times v. But lambda is, of course, an eigenvalue of A, so we can replace with A. But since A is symmetric, the place of A can be switched to the second place. But V is an eigenvector of A, so AV is equal to mu V. And we can take mu outside of the inner product. So we have this equals to this. Therefore, lambda minus mu times the inner product between u and v is equal to 0. But since we're assuming lambda is not equal to mu, so this is non-zero, therefore the inner product must be 0. So these eigenvectors are orthogonal to each other. And we are done. Next, we want to prove that any symmetric matrix can be diagonalized by an orthogonal matrix. By the way, an orthogonal matrix is something like this. So if M is a matrix, a square matrix, M transpose times M is equal to the identity matrix, then we say this M is an orthogonal matrix. And from this, by taking the transpose of both sides, we can also say that M times M transpose is equal to the identity. Now, suppose A is a real symmetric matrix, and lambda 1, lambda 2, and so on up to lambda n are its eigenvalues. And the corresponding eigenvectors are denoted as u1, u2, and so on. So these eigenvectors can be normalized, okay? Because if we have this equation, so u is an eigenvector, then if we multiply both sides by some constant c, let's say, then we have cu here, lambda cu here. So if u is an eigenvector, then cu constant times u is also an eigenvector. So the magnitude of an eigenvector doesn't matter. So we can always normalize each eigenvector so that we have the following. So just previously we have shown that different eigenvectors are orthogonal to each other as long as the corresponding eigenvalues are different. Then we can assume that the inner product between ui and uj is equal to Kronecker's delta. So that means it is equal to 1. So if I is equal to j, otherwise it's 0. So let's summarize this. A1 u1 equals to lambda 1 u1. And so on up to an un equals to lambda n un. So putting this into a huge matrix, so it's a row vector of column vectors. So AU1, AU2, and so on, AUN equals to lambda U1, lambda U2, and so on, lambda n UN. So this is a huge n by n matrix, and this is also n by n matrix. But this is a linear operation. Matrix multiplication is a linear operation, of course. So we can take this A out, and we have this matrix made of U1, U2, and so on, UN. And for the right-hand side, we can write like this: U1, U2, and so on, UN, times the diagonal matrix, lambda 1, lambda 2, and so on, lambda n. Of diagonals at 0. So we have this equation. Now let's define this matrix as U. So we have U on both sides, and this diagonal matrix as capital lambda. Then we have AU equals to U lambda. But this U, this matrix U, is actually an orthogonal matrix. So U transpose times U is this. So if we transpose this, we have U1 transpose, U2 transpose, and so on, UN transpose, times U1, U2, and so on, UN. So if we multiply these two matrices, we have U1 transpose U1 and U1 transpose U2, and so on, U1 transpose UN, and so on. And U2 transpose U1, U2 transpose U2, and so on. So as you can see, the diagonal elements are all 1 because of the normalization of each eigenvector. And off-diagonal elements are all 0 because of orthogonality of eigenvalues. So therefore, this is equal to the identity matrix. Therefore, this is U is an orthogonal matrix. And from this, by taking both sides, transpose of both sides, we also have U transpose is equal to the identity matrix. And now we have AU equals to U lambda. So if we multiply both sides by U transpose from the right, we have AU, U transpose, U lambda, U transpose. But this part is equal to the identity, and A times I is just A. So we have A equals to U lambda U transpose. So we are done. And another way to look at this equation is the following. So let's write U more explicitly. So U1, U2, and so on, and Un, and the diagonal elements, lambda 1, lambda 2, lambda n, and transpose of U. So U1 transpose, U2 transpose, and Un transpose. So if we expand this, we have lambda 1, U1, U1 transpose plus lambda 2, U2, U2 transpose, and so on. And this way of expressing the symmetric matrix A is called the spectral decomposition of A. So spectral decomposition. So spectral means so A is decomposed into different spectrum of eigenvalues. And this becomes using the sum symbol I from 1 to n and lambda I and ui times ui transpose. By using this notation, the application of a matrix to any vector x can be written as this. So applying this, we have I from 1 to n lambda I ui transpose times x. But this part is the inner product. So we can also write this as lambda I, the inner product between x and ui. But look, this part is the projection of x on ui. So what this means is that the application of the matrix A can be considered as this. First, we project x onto each eigenvector component, then scale that component by the eigenvalue. Then we add up all the contribution from each eigen component. And that is what A does to the vector x. Okay, that's all for this video. See you later. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.